Hi everyone, today I would like to present our paper FMHash Deep Hashing of In-Air Handwriting for User Identification. This paper has been accepted by ICC 2019. I'm Duo Lu. Consider you're wearing a VR goggle, surfing on the internet, visiting some website, and suddenly a dialog pops up asking to sign in. So this is pretty a trivial task on a desktop computer. Just type an ID and a passcode. However, in this case, in the VR scenario, you don't have a keyboard or a touch screen to type an ID and a passcode. So how can you sign in? Our idea is you write an ID and passcode in the air, and the VR headset has some motion tracking device, such as a 3D camera or a wearable device, to capture your hand motion. And the authentication server uses these information in the in-air handwriting to figure out which account are you logging in and authenticate your request. Gesture-based authentication is a well-studied discipline. So the question is how to input an account ID using a piece of handwriting. Note that the problem with ID is different from the problem with a passcode. For passcode, the system needs to answer a true or false question. So whether the authentication request is from the legitimate user or not. But for an account ID, the system needs to answer a multiple choice question. So the authentication system needs to figure out which account it is from potentially a large account database. Our solution is using deep hashing of in-air handwriting, so that the authentication server can build a hash table and convert a piece of in-air handwriting of account ID to a binary hash code. Using this hash code, the server can index potentially a huge database of accounts. And at login time, the user just writes the account ID in the air, and the authentication server can generate a compact binary hash code and use this hash code to search in the hash table to figure out which account ID the user is indicating. Our design goals contains the following. First, if the same user is writing the same ID string, then the system should generate the same hash code all the time. However, every time you write the same account ID string, your handwriting has tiny variations in speed and intensity. So our algorithm must be able to tolerate some kind of motion fuzziness, and the generated hash code is a fuzzy hash code. Next, the hash code generated for different writing should differ at least 2 bits, which means if they are from different accounts, the hash code should be different by at least 2 bits. And next, this fuzzy hashing method must be fast in both identification and training. There are a few technical challenges. First, we don't know what kind of features should be used to derive a binary hash code from the in-air handwriting signals. So in this way, we trained a deep neural network to automatically learn the features from the data. And next, it is generally difficult to train a deep model with very few data points because as an authentication system at registration, we don't want the user to repeat writing the account ID many times. Ideally, the writer can only needs to write it maybe 5 times. So to address this problem, we designed a data augmentation method, which is detailed in the paper. So our FMHash system works like this. The in-air handwriting motion is captured by a device, which is the lead motion controller in our case. The raw motion signal generated by the device is pre-processed to obtain a smoothed and normalized signal. And this normalized signal is fed into the deep neural network to generate a compact latent vector. And this latent vector is projected and quantized to generate a compact binary hash code. And the authentication server uses hash code to build a hash table so that login account ID can be retrieved in constant time. Here's an example of the hand motion signal. This is my handwriting of F, M, H, A, S, H, FMHash. And here's a motion signal. So we track the 3D position, speed, and acceleration. So this is an input of the neural network, input X. It contains 9 dimensions, and it is temporally normalized to 256 samples. So our neural network contains 5 convolutional and max pooling layers, and 1 fully connected layer. The output of the fully connected layer is called the latent vector H. The fully connected layer is connected to 2 paths. First, a softmax layer for pre-train the whole neural network to help these convolution layers to converge faster. And then the fully connected layer is connected to a projection layer, a special layer without a nonlinear activation. The output of projection layer is called the vector Z. Z has the same dimension as the final hash code. So if the final hash code has k bits, then Z has k elements. And Z is quantized to generate the final binary hash code. To train this neural network, we designed a progressive way. First, we pre-trained the neural network with a cross-entropy loss using softmax layer for 1,000 iterations, just to help these convolutional layers, just to help these convolutional filters to converge faster. And next, we trained the neural network with many batches of pairs. Pair of Z1, Z2. A pair of Z1, Z2 is generated by a pair of signal X1, X2, which means we ask the pair of input to run the forward pass of the neural network. And then, if this Z1, Z2 pair are from the same account, they have the label 0. If they are from different account, they have the label 1. Using this, we designed a pairwise loss function. So training this neural network is essentially minimize this pairwise loss. So this pairwise loss contains 2 terms. First, this one. This means if Z1 and Z2 are derived from a pair of signals X1, X2 from the same account, then D1 and D2, they should be close in L2 distances, which means minimize their distances. And if D1 and D2 are from different accounts, they should be separated by at least m in L2 distances. And these PQ are regularizers. We use this loss function to train the neural network for 1,000 iterations. And after that, we further fine-tune the network by 6,000 iterations with different alpha and beta weights. So let's have a look at the PQ regularizer. The PQ regularizer looks like this. Consider this is a vector space of Z. This PQ regularizer put a grid of 2 to the k. This PQ regularizer places a 2 to the k grid space on this Z vector space, like this. So this shaded area are the areas created by the PQ regularizer. In this way, each element of the z vector is going to be placed in the region minus p to minus q, or from positive q to positive p. Similarly, in another direction, in another dimension, minus p to minus q, or positive q to positive p. After quantization, this part is minus 1, and this part is plus 1. Similarly, this part minus 1, this part plus 1. If for a pair of projected vectors z1 and z2, if they are from the same account, they should be placed in the same grid space. But if they are from different account, they should be pushed away by m distance. By careful choosing this m, we can put the z1 and z2 from different accounts into different grid places. For example, if we choose this m to be p times square root of k, so p times square root of k is this distance from the origin to this point. So that if two projected vectors z1 and z2, they are from different accounts, so we ask them to be separated at least this amount of distance. In this case, by minimizing this loss function, they would be most likely guaranteed to be pushed into different grid space. So this regularizer works in theory, and in practice it also works. So this is a visualization of the first two dimensions of the z vector on our dataset, and the histogram of the elements of the z. So once this neural network is trained, we can use it to do identification. Consider each account has an ID, a hash code BID, and a vector HID. We build a hash table with all the accounts under a tolerance value L. So if the tolerance value L is 0, then this BID, the hash code of each account, only occupies one bucket in the hash table. But if L, the tolerance value, is 1, then the hash code BID of each account can occupy k buckets by varying each bit in this hash code. So this means 1-bit fuzziness. For example, here's a Hamming space, and we have 4 accounts, A, B, and C, D. So the radius of this circle is tolerance value. This means in the Hamming space, one account can occupy more than one bucket if the tolerance value L is not 0. This means you have a fuzziness regions, and there are cases that two accounts have overlap of fuzziness regions. Now at login time, given the hash table and the identification request xi, we generate a hash code bi using the neural network and the vector hi. Then we run a hash table search using this bi. Because of the collision of fuzzy regions, we may get a list of candidate accounts, ID1, ID2, and so on. And next, we run the nearest neighbor using the H factors to narrow down to just one account. For example, consider these black dots are the BI. And there are cases that the BI can hit one account or more than one account. There are also cases that BI does not hit any accounts. So if BI is from account C and it hit account C. This is a true positive of account C and true negative of all other accounts. But if BI is from account D, but it hits account C, then this is a false positive of account C and a false negative of account D. We also call this a misidentification. There are also cases that BI doesn't hit any accounts like this. In this case, we call it a failure of identification. This is also a false negative of all accounts. So we evaluate our system with a dataset collected by us. A dataset contains 200 accounts. For each account, we ask the user to write an ID string 5 times for registration and another 5 times and as 5 independent identification requests. So here are the results. We can see the performance is pretty satisfying. So we can achieve in most cases more than 99% precision. If we increase the tolerance value, which means we use larger search range, it helps recall, but it hurts precision. This is reasonable because if we if we increase the search area, potentially there are less failure to identification, but more misidentification, especially the misidentification because of a collision of fuzzy hash regions. And in our case, misidentification is usually more harmful, and hence we favor precision than recall. Here's the results of misidentification and failure of identification. And here's an example of the generated hash code by writing this FMHash. So note that the hash code is not deterministic. This means if you retrain the neural network, the hash code would be different. And here's an example of the spread of the hash codes. In this case, we plot the hash code of all accounts in 2D space. The first dimension is lower 8 bits, and the second dimension is higher 8 bits. We can see the hash code of all 200 accounts are kind of evenly spread in this space. And next, we evaluate the hash code fuzziness. So if 2 hash codes are generated by 2 signals from the same account, then 94.4% of cases they don't even differ any bits. So only slight chances that they differ more than 2 bits, which means the fuzziness can be controlled to some extent. On the other hand, if the 2 hash codes are generated from signals of different accounts, 99% of the cases these hash codes differ at least 3 bits. So at last, we have a look at the quality of the hash code bits using a 16-bit hash. So first, we show the distribution of 0 and 1 in each bit of the hash code. We can see each bit roughly has the same chance to be either 0 or 1. This means the generated hash codes looks pretty random. And next we show the correlation of the hash code bits. We can see they don't have a strong correlation. This means each bit contains some information which is independent from other bits. This all means that the generated hash code has a pretty good quality. They have low chances of a collision, and they are quite spread in the Hamming space. So at last, conclusions. So in-air handwriting, in our opinion, has a good amount of information to distinguish different users in a database by using this fuzzy hashing method. and minor movement variation can be tolerated to some extent without much loss of discriminative capability by our careful design of neural network architecture and the training method. So there are limitations. First, our current dataset is pretty small, so a larger dataset might be needed for more rigorous evaluation. And now, adding new accounts requires retraining. Question is, can we design a deterministic feature encoding method so that when new accounts are added, we don't need to retrain, at least retrain the projection layers? So this will be addressing our future work. We believe we can. And another question is, can we generate cryptographic keys from this fuzzy hash? And this will also be addressing our future work, and we believe we can do it. Thank you.